this is Calvin, and I'm teaching you frequently differentiating inverse functions. And I'm just gonna make one point clear. This right here is a reciprocal. So let's say you have a value here, and initially x is equal to, let's say, 3 over 2. A reciprocal is a flipped over version of that. So that would be 2 over 3. That would be that. That's irrelevant to our for this lesson. But what you need to know is that there's a difference between this and that. This is an inverse function right here. So what it's saying, essentially what it means is, you see this question right here, y equals to 3x. That's the original equation. When you put the inverse right here, that -1, that means that this equation right here, it's like a xy, right? You swap the values to get like y, x. So pretend this y is x to x over 3. So that's what an inverse is. You just swap the values, not essentially swap, but you just exchange it, and you just make y go by itself again. You factor and do whatever you want, whatever you can to make y go by itself. And I guess that's for that part. And then the thing you gotta remember for solving these types of equations is this equation right here. Alright, so I'm gonna show you what this equation means for up and over here. So what this means is that I'm gonna show you a couple examples of how this works, and so you get a gist. I really recommend writing this down whenever you have to differentiate a inverse. So I'll take you there. So I changed my angle just so you can see what I'm doing. Let's look at the problem that we're gonna be working on. Okay, so this is our problem, and what we gotta find is g prime of -2. And as I said earlier, look at all the fine text. Gx is equal to f inverse of x. So I'll just write it down for you guys. You don't have to write this down when you're practicing. Well, you can, but when you're in the AP test, I don't recommend doing that because time is so precious. And oh yeah, so let's find, what's it, g prime of -2. So prime is equal to derivative, right? It's a derivative, and also gx is equal to f inverse of x. So what's that? Derivative, and then f inverse of x, of f inverse of -2. Okay, so I recommend writing this equation, the one that I taught you earlier. Is that d over dx, which is derivative. What's that? I don't want to say it because it'll probably ruin this recording. But yeah, just try to remember this. Yeah. I recommend like taking a picture with you, like in your phone or something, just if you forget when you're doing an equation. Okay, so what we got to do is just plug in that -2 over here. So 1 over f prime of f inverse of -2. And okay, so whenever we were doing these types of problems, they're always gonna try to trick you. So you might go for this one, but that's derivative. That's nothing to do with us, with what we're trying to find, which is f inverse of -2. So ignore that because it's derivative. And also here, it might trip you up because it's f of -2, not inverse. When it's inverse, you have to look at the y first. So f -2 is equal to 3. And yeah, so that'll be f of, no, 1 over f prime of 3. And it's already given what f negative prime, f prime of 3. That'll equal to 5. So that'll equal to 1 over 5. And I guess that's it. That's our lesson. Peace out. Okay, so hi, this is Calvin, Austria, and I'm gonna be teaching you 3.3 differentiating inverse trigonometric functions. It's kind of long, but it's basically the same thing. You just have to remember a few equations, and yeah, that's it. So what I'll be teaching you first, just so you remember, is what arc means. So this only applies to trig stuff. So what is this? So arc, right? You might see like arc sine or like arc sec or like cosine or like tan or whatever. That basically means for here sine inverse, and like for sec that'll be sec inverse. That's just something to know. Just yeah, it's just a very small thing, but if you see arc, it just means inverse of like a trigonometric blah, blah, blah thing. All right, so now for the hard part. That's the easy part. So there's 6 equations that you gotta remember. All you need to know is 3, and then you already know you'll already know the rest. So I'll just write them down and show you what they mean. So this one, it will be 1 over square root of 1 minus x squared, and this one will be equal to 1 over absolute value of x. What's that? X, the square root of x minus 1, and this will be just equal to 1 over x squared plus 1. How about like these ones? I'm gonna show you these ones. Like cots or like cos. What's cos? What am I doing? Okay, so cos inverse, and what does that equal to? Or like cosecant inverse or cotangent. What do you do for that? So whenever it starts off with a C, it's so easy. All you gotta do is just negative, negative, negative. That's all you gotta do. And that's how you know. All you need to know is basically 3 equations and the negative for the C's, and that's it. Yeah, let's go to some problems. I'll show you some problems right now. 3, 2, 1. All right, so change camera angles so you can see what I'm working on. And what we'll be working on is 3 equations, 3 problems. So the first problem is this: arc sine x at x equals to, what's that, square root of 3 over 2. So basically what that means is that what's that, sine of what angle, theta, is equal to square root of 3 over 2. And what you gotta remember is the unit circle. Oops, sorry. The unit circle, you just gotta remember that. If you don't know the unit circle, look at other videos. This is not the one for you, but when you're working on sine, you gotta focus on this part of the circle. So you just gotta remember it. Ooh, when is the sine square root of 3 over 2? And that'll be at pi 3. So that'll be our answer. So like, you know, sine pi 3. Or just make sure, you know, you can check this in the calculator. Oh, that'll be square root of 3 over 2. So that'll be the answer for that. That's our answer. Square root of pi over 3. And let's look at the next one. The next one is, what's this? Cos inverse. Yeah, cos inverse at x over 4 and x equals to negative 2. So let's put that negative 2 over here. Negative 2 over 4 is negative 1 over 4. No, negative 1 over 2. And so at cos, what's that? So let's write it down. Cos theta, right, equals to negative 1 over 2. And you gotta remember your unit circle, and that'll be at 2 over 3. So like square root of, no wait, no, just 2 over 3 pi. So yeah, that'll be cos 2 over 3 pi is equal to negative 1 over 2. And this is our answer for that. And then for tan, arctan, let's write it down. Tan inverse of theta, right, is equal to, what's that, 1 over 3? 1 over square root of 3. And so what that means is that you know, if this is kind of hard for you, you can split it up, because it's most likely that you don't remember the tans. So you know what tan is? What is that? Sine over cosine? Sine theta over sine, over cos theta is equal to 1 over 3. And then you got to do some math over there in order to find what that is equal to. So that will be equal to what's that, pi over 6. You can just review this over and over just so you can remember the tans. Look at a different video so you can remember the tans. So that's basically it. You know, we just looked over how the simplicity of 3.4, tan, cos, and arctan. And then remember when it's like cosecant, cos, and like cotangent, you gotta do negative for that. And that's basically it for that one. So that's basically it. And turn it off. Peace out.
Hello, my name is Santiago Rios, and I'll be looking over 3.5. 3.5 essentially looks over, makes you work with multiple derivative rules in one equation at once, and you need to know how to list out all of these different derivative rules that we learned between Unit 2 and 3, and use them in an equation of your own. Okay, so I have an example right here of a multi-derivative equation. Sorry for the coughing and nasally-ness in my voice, as I am not feeling so well right now. I'm actually currently ill, so please bear with me on that part. So to start, we're going to list all the derivative rules that we can find here. So we're going to clearly use products rule. We're going to abbreviate that a bit. Pro. And then we're going to use power rule. Power rule. Chain rule. Chain right here. And implicit differentiation because of the y. This was also going to kind of abbreviate. And constant rule. Let's disagree with that. And essentially, you also need to know what to do with a cosine and natural log, how to direct those two. And so, knowing this, we can now move on and solve this equation. So, first thing we need to do is to basically simplify this on put the square root on the the square on the outside. So put cosine of x, and we're gonna put the square on the outside so it can make this more obvious that this is chain rule. And then we're going to actually solve that. So knowing product rule, this is going to be f, this is going to be g. And in product rule, you have to do f prime of g, this is times, plus f times g prime. Whereas chain rule, let's do. Sorry. Yeah, to do f prime of t inside of f prime times g prime. In this case, this is f, or no, this is not f. This is g, and this is f. Okay, let's actually solve this. Okay, so this is going to, in fact, this is going to derive out into essentially how we got this was through the table. We derive square root 2. 2 is going to go in the front. Cosine of x is going to be in the middle. And then you have the g again, which is cosine of x. And that's going to be negative sine of x, making it a negative 2. And then you have ln of x because of just regular g. And then you add that with cosine squared of x over x, which is gotten by, of course, not deriving this, and deriving natural log of x, which gives you 1 over x. And then you just multiply that to get that number. And then, of course, with the implicit differentiation and power rule, you just multiply 3 to 8, 24, minus 3, or 3 minus 1. It's going to give you 2. And then you put the dy over dx because it's a y. And then you make that equal to 0 because 45 has a coefficient, so it's 0. And so now what we're going to do here, to further simplify this, and to isolate the dy, the implicit differentiation, we're going to add all this to this side and subtract this to this side. And that's essentially going to look like something like this. Factor this out. That's going to leave you with nothing here, then 12 down here. And so let's prevent this to get our final answer. And that's your answer. Hopefully you learned a lot about using multiple derivative rules and one equation. And this is Santiago Rios. Signing out for this one. Alright, hello, this is Santiago Rios again. Again, sorry for my nasally voice and coughing throughout the video as I am ill right now. But we're going to be demonstrating higher order derivatives in unit 3.6. As this unit essentially just explores how you're able to essentially find a derivative of a derivative. And this can be essentially done for most of any sort of derivative. And this will be, and similar to like 3.5 with like equations with multiple derivatives, that will also have a, you could also twice derive, triple derive, fourth derive, all those. So there isn't really no limit for higher order derivatives. So I pick out this example as I thought this would be a pretty good way to demonstrate this idea. And we're going to be deriving this 3 times. And so essentially we're going to start off with 1. And this is pretty simple stuff, or simple kind of derivative. And you can actually do this in your head if you really understand the rules, but I'm going to show it step by step. And essentially, this is just going to be regular power rule. Of course, this is going to be x over negative 2, as this is a fraction. And this will leave us with negative 2x negative 3, which will give us negative 2 over x cubed. Okay, and so now let's get this, and now let's find the derivative of this. And that's essentially just higher order derivatives, finding the derivative off of another derivative. And so this is going to be basically derivative to essentially the second degree. And that's going to be prime of x equal to, essentially this is going to be following same rules. So we're gonna get -2, negative power to -3. We're gonna do power rule. That's gonna give us negative 6x to the power of -4, and that'll leave us with 6 over x to power of 4. And then for our last higher order derivative, it's essentially just the same thing. But now we're taking the derivative of this. So that's going to be... And that's kind of essentially all you need to really know about higher order derivatives. They essentially take the derivative of the derivative you had prior. And these could actually go up for essentially forever. So this would be like pi to the 4th degree, 5th degree, 6th, 24th, which I'm not sure if you're ever gonna need that. But you know, if you really need to do it, you can always do it, because essentially you're just taking the derivative of the derivative before to find, you know, the 24th degree of the derivative. And that's essentially all you need to know about 3.6, and that's the example that I gave.
All right. Hello everyone. My name is Gaspar, and that's a very flattering picture of me. We're going to be covering L'Hopital's rule. Basically, L'Hopital's rule is helpful when dealing with limits. When when it equals 0 over 0. So for example, let's say we have x squared minus 7x plus 10 over x minus 2. If we directly substitute, what is going on? If we directly substitute, that would equal, let's see. Basically, L'Hopital's rule just helps with finding limits. And dealing with 0 over 0 and infinity over infinity. Infinity, that's an 8 over infinity over infinity. There we go. What it says is that when it equals 0 over 0 or infinity over infinity, you're allowed to take the derivative of that and substitute a. So let's do that. So then it would be limit as x approaches 2 equals 2x minus 7 over 1, which would equal -3 after direct substitution. I forgot the 2. You substitute right there, and it would equal 3. So the limit as x approaches 2 would equal 3, thanks to L'Hopital's rule. Okay, so I forgot to mention, but you could use L'Hopital's more than once if you get 0 over 0 again. So in this example, 1. So using L'Hopital's, that would be sine of x over x squared as lim x approaches 0. That would still equal 0 over 0. So you could just keep doing L'Hopital's until you get an answer. Allegedly, you shouldn't do it more than 3-4 times. If you get 0 over 0 that many times, I think you should just give up and accept that it's 0 over 0. So let's do it one more time. Yeah, you could just keep doing it repeatedly. Pretty helpful when finding limits. And I believe that's all there is for L'Hopital's rule. I lied. You can use it when looking at examples that equal infinity over infinity. So, really quickly, limit infinity over infinity. There. I don't know what the white squares are. Okay, whatever. Limit as x approaches infinity. Take the derivative, so that's 4x over 2e to the 2x. That would still equal infinity. So we do it one more time, infinity over infinity, because you plug it in. So one more time, we go limit as x approaches infinity. That's an infinity, just trust me. It's now 4 over 4 e to the 2x, which equals 1 over e to the infinity, because that's an infinity. Apologies. My handwriting is terrible, I'm sick. E to the infinity, which would equal 0. So yeah, I believe that's all there is for L'Hopital's rule. It's pretty handy little thing, pretty helpful, and I hope my sick explanation helped a lot. Like and subscribe for more helpful calculus tips.